Now, there's nothing difficult with that. However, observer B is standing on the side, watching the train go past, and observer B sees, hang on, that's not what happens. Because the train is moving, it seems like the light takes longer to get to the woman from the left-hand side than it does from the right-hand side, because the train is moving. So two events are defined to be simultaneous if an observer measures them as occurring at the same time, such as by receiving light from these two events, turning on the light at both ends of the carriage. We won't go into details as to how they're turned on, but this is a thought experiment, remember. This is not... I'll keep going. Two events are not necessarily simultaneous to all observers. The relative velocity between the observers affects or influences whether the two events are observed to be simultaneous. Now remember, this is not to do with perception. My perception of this screen is that it's got a nice green tinge to it, but your perception might be, no, it's got an orangey tinge to it because you're colourblind or something, or bluey tinge or yellow or something. We're not talking about perception. We're talking about this is actually reality. And we're not dealing with speeds of train carriages that go, 60 or 80 kilometres an hour, which makes, we're actually dealing with fast trains that go close to the speed of light. Simultaneity, that's the noun for simultaneous. Simultaneity is not absolute. Now, if we use the arrival of light to measure the time interval between the two flashes of light produced by the flash lamps, then we find that the two flash lamps for observer A, who's midway between them, are on the rail car that moves to the right relative to the observer. But observer B arranges for the flashlights to be emitted just as A passes B, and both A and B are then equidistant from the lamps when the light is emitted. Okay, so you can see in the first picture, they're just passing each other and the light gets emitted. But as the carriage is going past, it's the light from the left catches up, so to speak. And observer B measures the time interval between the arrival of the light flashes. And according to postulate 2, the speed of light is not affected by any motion of relative. Therefore, the light travels equal distances to him at equal speed. And observer B measures the flashes to be simultaneous. Okay. Now, all that, you can see there's a link at the bottom. You're welcome to follow the link and get a little bit more information if you want. But what else can we say? What does observer B see happens to observer A? Observer B sees light from the right reaching observer A before the light from the left because she has moved towards the flash lamp, lessening the distance the light must travel, reducing the time it takes to get to her. So light travels at speed c relative to both observers, but observer B remains equidistant between the points where the flashes were emitted, while A gets close to the emission point on the right. From observer B's point of view then, there's a time interval between the arrival of the flashes to observer A. In observer A's frame of reference, the flashes occur at different times. And we come back to that's better. Here's the question. A car passes Erin at 20 meters per second. She compares the rate that the clock in the car, so I just need to move that out of the way. Let me just read that again. She compares the rate that a clock in the car ticks with the rate of the ticks on her own watch that she's wearing. What is the ratio of the two rates of time in the different perspectives, and what do you conclude about time dilation at low velocities? So we're dealing with 20 meters per second. That's not really fast. Let's have a look Here's the first step. Data, v equals 20 meters per second. Yay! And we want the ratio of the two rates of time. So t over t0. I'll just put a note this step carefully. This is the equation that we're using. It's the funny looking thing, and we just come back to going, it's based on Pythagoras' theorem. But it relates t with t0. Remember, time measured in different frames of reference. Substituting, and we've got t over t0 is what we've got on the left-hand side. Substituting in the bottom, we've got 20 meters per second for v, and the speed of light, 3 times 10 to the 8 meters per second. Of course, square both, see what we come up with. Now, I put a little note there called gamma. Gamma is sometimes a shorthand term for that complicated looking square root thing. We have, by calculating, and I hope you've got a calculator with this many decimal places. I know you don't, but the one on my computer does. 1.0000000000000000222, and so on. Okay, what do we conclude? Therefore, when v equals 20 meters per second, the difference between the rates of time in two perspectives is so small that it's difficult to calculate and much more difficult to notice it. So the ratio of time for stationary errand and looking at a clock in the car going at 20 meters per second is really, really small. So for all intents and purposes, when we're dealing with normal speeds that we drive at, relativity doesn't have an effect. Okay? And which is why Newtonian physics actually works. Newton's laws of motion work. They have to be nuanced when we're going really, really fast. But as we're just driving along and the police pull you over for speeding, they wouldn't pull me over for speeding, of course, but, you know, if you get pulled over for speeding, you just go, well, you can't pull out Einstein's theory of special relativity at this point to say that their clock's going slow or something, because that's just not true. I've got a cute little graph to help explain that here. Now, this is the ratio, V on C, on the horizontal axis. V on C, if you think about it, is the proportion of the velocity you're traveling at relative to the speed of light. So it must go between 0 and 1. Now, if you're traveling pretty much, so about where it says 0.2 times the speed of light, it's really okay. Newtonian physics will get us through. The vertical axis is the gamma. In other words, it's the amount that the time dilates. And you'll notice that gamma, as you're approaching 0.8 of the velocity of light, then it starts to increase from 1 to 2. And after 0.8, it suddenly jumps up so that when you're going, well, there's a point there at 0.994 times the speed of light, then gamma is a massive 9 times. So there's sorry, I meant massive, meaning just a huge amount. We know that relative to each other, clocks run at different rates, okay, relative to each other. Okay, the clock in one frame of reference will always tick at the same time, and that same clock moving faster will also tick at the same rate. So clocks do not slow down. Okay, they do not. But when you're in one frame of reference and you're looking at the other frame of reference, so we're dealing with two different people, two different frames of reference, whatever, then one clock runs at a different rate, looking from the other frame of reference. That's what that first sentence is all about. Now, planes travel about 1 million times more slowly than c, and you can see the result for gamma is one with lots of zeros. But atomic clocks are very precise, and so even one point with all those zeros can actually be measured. And that was the basis of a very bizarre experiment. 1971. So this is almost 70 years after Einstein came up with the theory of special relativity. Okay, this is after 2 world wars plus subsequent disturbances and wars and whatever. These two guys, Joseph Hafele and Richard Keating, so it's sometimes called the Hafele and Keating experiment, took atomic clocks onto planes traveling both east, and with the Earth rotating in the same direction underneath them, we could call these the slow frames, and west, and these planes have the Earth's rotation speed plus their own. And then they return to where they came from. Now, if you've ever flown overseas on a long distance trip, you will know that we're talking about time zones and things like that. But Hafele and Keating were actually describing relative motion. Okay, so apart from complications due to gravitational field variations and their own acceleration, which we don't deal with in HSC physics, but is covered by Einstein's theory of general relativity, it gave results in agreement with the relativistic prediction. Okay. And if you want to have a look at that for yourself, I've got the reference there, and there are diagrams and discussion about this experiment with a hyperlink just for you guys. So if you're on the slides, you can click that and it'll open up in your browser. Okay, so that's the first evidence, and it validated Einstein's theory of special relativity. So it's called the Hafele and Keating experiment with atomic clocks on planes. There was actually a third set of clocks that were actually left on the airport rather than flying around the world. Okay, second evidence I mentioned in passing, particle accelerators. They generate short-lived particles, and they're called, we'll get to know these names, muons or pions, depending. But needless to say, when you're looking at muons and pions, they travel at a fraction of percent of c, and in the laboratory frame, they survive what seems to be much longer than their lifetime. Now, muons and pions have a half-life, a bit like radioactivity. And within that time frame, you'd expect so many of these particles to decay. But when you're looking at it from the lab, remember the lab is stationary, which doesn't mean that at all. It just means the laboratory frame of reference. Relative, it seems like these particles survive longer. Muons have a half-life of 1.5 microseconds, so your wristwatch won't do. Muons are formed several tens of kilometers above the Earth in the upper atmosphere by cosmic rays. So cosmic rays hit the atmosphere, suddenly got these things called muons being formed. They should only last 1.5 microseconds as they're traveling the 50 kilometers at the speed of light. And it should take, 170 microseconds, which is the equivalent to 110 half-lives. And so we would actually expect their numbers to be reduced by a factor of thousands. Okay, so effectively on Earth, which is our stationary frame of reference, we would expect to see no muons at all from 50 kilometers above the Earth where these muons are formed. That's the expectation. The reality is you can measure them at sea level and at various altitudes with the rates that agree with relativistic dilation of their half-lives. Now, we'll do an example in more detail later. But this is evidence that Einstein's theory of special relativity actually happens. Okay, so time dilation happens despite how counterintuitive it may seem at first. Okay, so that's where I'm going to stop this afternoon.